Jai Hind students, in today's lecture, we will cover a very important topic, that is canonical cover. So in this topic, in this lecture basically, we will understand the algorithm and the example to calculate the canonical cover. You know already what is the canonical cover. Canonical cover is nothing but the minimal set of functional dependency. So a functional dependency set will be given to us and we need to find out the minimal set of functional dependency from that. So that is what the canonical cover. So we are having a set of steps to calculate the canonical cover. Right. So in the first step, understand the algorithm very well. You will be able to calculate the canonical cover very correctly and your result will not be wrong anytime, right? So in the first step, what we need to do for a given function dependency set, what we need to do? We need to decompose each functional dependency using the decomposition rule. We have already studied the Armstrong axioms, right? So if the right side of any function dependency has more than one attribute, then we need to decompose this, right? If it is having one only, then there is no decomposition, obviously. Okay, in the second step, what we are doing now, all the decomposed functional dependency will make a new set of functional dependency, right? And in the third step, what we need to do, then after making this new set, what we are doing, we need to find the closure of the left side of each of the functional dependency by including that functional dependency and then excluding that functional dependency, right? And we'll check then if in the both cases we are finding the same attribute closure, right? Then we will say that that functional dependency is redundant and we need to remove that. If we are not finding out the same closure using that functional dependency, it means we cannot exclude that functional dependency, right? That is important one. We need to repeat this step again and again for all the functional dependencies exist in the new functional dependency set. That is the step 4. So we have, once we have done for all the functional dependency, what we need to do, we need to check the redundancy of attribute on the right side of the each and every function dependency. Okay. So how we will do it? By selecting those function dependency set which are having more than one attribute on its left. I said right, but it is left basically if we are having this functional dependency. So we need to check redundancy here at the left side. So for this, we need to compare the closure of all the attributes combinations. If it is not same, it means that attribute or set of attribute is important and cannot be removed. Okay, otherwise what we will do, we'll remove because that attribute is redundant attribute, right? So this way we can find out the canonical cover for any given set of functional dependency. So these are the steps by which if you are following these steps, you will not be wrong by in calculating the canonical cover. This canonical cover calculation is very difficult for the student if they are not following these steps, right? Now we need to understand the these steps by one example. So here we are taking one example. Here we can see that the function dependency set is given to us. So this is what, this is nothing but the given set of functional dependency. How many functional dependencies are given to you? 1, 2, 3. 3 functional dependency set is given to you and now you need to find out the canonical cover for this functional dependency set. Now if we are following the step 1, okay, so in the step, according to the step 1, what we need to do basically, we need to decompose the function dependency at the right hand side if we are having more than one attribute at the right hand side. See, the first functional dependency said B tends to A. Not more than one attribute at the right hand side, so no decomposition, obviously. And if we see the second functional dependency, AD tends to BC. Here we will decompose this functional dependency according to the Armstrong axioms decomposition rule. So we will found these two functional dependency from the second given functional dependency, right? And see the third functional dependency, C tends to ABD. Now what we will do, we will write C tends to A, C tends to B, C tends to D by the decomposition rule. So how many function dependency now we are having? We are having these 6 functional dependency. So in the step 2, what was the step 2? We need to make this new set of functional dependency. This new set of functional dependency is what? It is the same, right? So till step 2, we have covered our algorithm. Step 3 was very important. Now, in the third step, what we need to do? We need to pick up each and every functional dependency one by one, and we need to check the closure of the left hand side attribute. So, in the first step, what we will pick? We will pick this function dependency B tends to A. Okay. So, we'll pick this function dependency, and when we are picking this function dependency, what we need to do? We need to find out the closure of B. Okay. So, we'll calculate it by, okay. So, what we need to write? All the functional dependency. B tends to A, AD tends to B, AD tends to C, C tends to A, C tends to B, C tends to D. So, in the first step, we know we need to calculate the functional attribute closure of the left hand side of the attribute of this function dependency, and we need to include this function dependency also, this one. So, this is the first step. Now, by excluding this function dependency, we will again calculate the closure, right? So, in that case, what will be our set? We will exclude this, right? So, we will write AD tends to B, AD tends to C, C tends to A, C tends to B, C tends to D, right? Now, calculate the B1. I will write here. So, when I am writing B plus, it means the closure of B. So, if we are having B plus, so we are starting with the B, and if we are having B, we can reduce A. Okay, so A also can be reduced. So, in the closure, we will add A. Now, we are having BA with us. So, D is not with us, so we cannot reduce anything here. We here AD, D is required to reduce C. No, we cannot reduce anything. Now, we are not able to reduce anything here. Okay, and then we'll check the closure of B again. So, we are having B, we will write B here. We'll check the closure again by eliminating or excluding this functional dependency, right? So, what we will able to reduce here? We are having B only, so we can check nothing can be reduced. Okay, so nothing can be reduced. So, we'll check here the closure is different in both the cases. So, what will be done then? It means what? We cannot remove this functional dependency. It is important, right? Why it is important? Because if we remove it, then we are not deducing anything. If we are having it, we are deducing this A, right? So this closure is not same. Okay. So this is important one. So in the step 3, we were checking first functional dependency and I found it important. So after step 1, we will write these functional dependencies. New set. What we have find? We are not able to remove it, and AD tends to B, AD tends to C, C tends to, what was there? C tends to A, B, D. A, C tends to B, C tends to D. So nothing has been removed till now. Now we will repeat the step 3 for this functional dependency. Okay. So we are on the step 3 only. Right. So in this again we will check for this functional dependency. So we will calculate the closure of AD with the set of excluding this functional dependency. AD tends to B. Okay, this is also here. B tends to A. AD tends to C. C tends to A. C tends to B. C tends to D. Okay. And again, what we will do? We will find out the closure without this, excluding this. So, for that case, we will write AC tends to C, C tends to A, C tends to B, C tends to D. Okay. 2, 3, right. Okay. So here we are calculating AD plus, means attribute closure of AD. So if we are having AD, it means AD we are already having. If we are having AD, we can deduce this B. Okay, right. So we will write B. If we are having B, we can deduce A. A is already here. If we are having AC, AD, then we will deduce C. So C we will include here. If we are having C, we can deduce A. A is already here. If we are having C, we can deduce B. B is already here. If we are having C, we can deduce D. D is already here. So what is the closure here? A, D, B, C. A, B, C, D. Right. Now we will calculate the closure without having this functional dependency. We are excluding it. Now we'll calculate. AD is already here. If we are having B, no, we are not having B, so nothing can be deduced. AD hai. This is AD. So AD tends to C. If we are having AD, we can deduce C. Yes, we can deduce C. If we are having C, we can deduce A. A is already here. If we are having C, we can deduce B. B is not here, so we will write B here in the closure. Okay. If we are having C, D can be deduced. So D is already here. So what is the closure? This. So we can check here, both are same. It means if we are having this functional dependency, then also closure is same. If we are not having this functional dependency, as we have excluded from the set, then also we are gaining the same thing. It means no importance of this. If this function dependency is not here, then also we are not having any impact of on the function dependency set. So what we will do, we will remove it. So after removing it, we are having new set B tends to A. It was important. This is not important. So we are removing this. Now we are having the set, this one, D. Okay, so we are having this. This is the new set. Till now, we were able to remove this functional dependency only. Okay, so we have checked for this. Now we will check for this. Okay, so in this step only, we will check AD plus with all the functional dependency set. So this one, right? And then we will calculate the functional dependence, attribute closure of AD without having this. So we will write this. C tends to A, C tends to B, C tends to D. Fine. So when we are calculating this, so AD is also already with us and we are having AD, then we can deduce C. Yes. We can deduce B also. If we are having C, we can deduce B also. So all the attributes can be deduced by this if we are having this function dependency set, right? Now, see carefully, we are again calculating the functional, we are again calculating the closure of this AD without having this function dependency. We have removed from here, right? So here AD we are already having. Now we can see that if we are having B, no, we are not having, so we are not able to deduce anything from this. We will check this. C, we are not having. C, we are not having. C, we are not having. So we are not able to deduce anything. So from here, we can see these two functional dependency sets are not same, right? So we will be able to remove it? No, we will not able to remove it because we are not getting the same. If we have this functional dependency, we are able to deduce more attributes. If we are not having this functional dependency, we are not able to deduce anything, right? So this is what the important to understand. Now, we will remove it or not? No, we will not remove it, right? Okay. So now, the new function dependency set we have, we need to write on the next slide, I think. So, okay. So, we'll have B tends to A, AD tends to C. We found it important in the last step, right? And the other one A, B, and D. Okay. Check again. Yes, it is correctly written. Okay, so now we have this set. We are not able to remove this or this. Now we'll check for this functional dependency set in the step 3 only, right? So for this, what we will calculate? Closure of C with the having all the functional dependency set. C tends to A, C tends to B, C tends to D, right? And we will calculate the closure without that. B tends to A, AD tends to C. We will not include this, right? So we'll write these two. Okay. So C we are already having. So if we are having C, we will be able to deduce A, B and D. A, B and D. So we are getting this, right? Now, in this, what we will be able to deduce? C we are already having. If we are having C, we will not be able to deduce anything from here. Nothing from here. B can be deduced if we are having C. D can be deduced if we are having C. So, check these two set of attributes are same or not. Not. Okay. These are not same. Right. If we are having these attribute closure not same, it means what? It is important. It cannot be removed. Right. So the function dependency set is same. So it is important. We have already found it is important. It is important. So now turn on this. Let's check for this functional dependency. To check for this functional dependency, we will again calculate the closure of C with the set of B tends to A, AD tends to C, and C tends to A. We are checking this one, right? So we will include here, while calculating the closure of C, we will exclude here that functional dependency. Which one? This one. We will not include it. We will not include in it, right? So we will calculate the closure by this and by this. So if we are having C, we can reduce A, B, D, A, B, D. Yes. If we are calculating the closure of C, it means we are having C already. If we are having C, we can reduce A and D. A and D. B, we cannot deduce from this set because we have removed this. We have excluded this. So we can check again, not same. So this functional dependency is important for us. Right. So now this is also found important. We will check this, the last one. For this, we will calculate the function closures of the left hand side of that particular functional dependency. That is nothing but the C. So we'll make out the closure of C by having all the set of functional dependency till now. C tends to A, C tends to B, C tends to D. Right. And then we will exclude this one from this set. B tends to A, AD tends to C, C tends to A, C tends to B. Not able to write properly. So I'll erase this. And then, okay, C tends to B. Will not write this C tends to D. Okay, we will exclude it. Now calculate the closure of C. C already we are having here. So if we are having C, we can reduce these, this, A, B, D. Again, same. Okay. In this case, we are having C. So if we are having C, what we can reduce? A, B, and now nothing. Okay, nothing can be deduced. Okay, here A, B only. A, D. D cannot be deduced anyhow. So these two sets are not same. Not same. So this is what the important one. Right. So it is also very, very important and we cannot deduce. Let's check this one again. We have checked it is important, but we can check the again A, B, D. We can have here we are having okay A, D. Then C, not same, right? So no issues. We have found all the dependencies important, right? So here we have the set. This one, A tends to B, AD tends to C, C tends to A, C tends to B, C tends to D. right? So this we have deduced till now. Again, we can check the steps if we are wrong somewhere. Yes, we have found it is the same. Okay, in the new set, we check for this. So this is removed, but this is not same, so we have not removed it. Yes, it is correct. We are checking again all the steps basically, and C tends to A. So we are checking A, B, D. Yes, if we are having C without this A, so what B, D. So C, B, D. Okay. No. So when we are checking this, so here we can see that C is already having, B and D can be deduced. Oh yes, here we can see we can reduce D also. Here in this set we can reduce D also, right? So C we are already having. If we are having C, we can reduce what? B. Okay. Right. If we are having B, we can reduce A. Yes. From this functional dependency, we can see that if we are having C, we can reduce D. So, by mistake, we have written not same, but again, when we have checked, it is found the same, right? So, this is not important at all, right? And again, we will check it the same. Yes, not same. We can check for this. Not same. So, while we are rechecking the things, we will found it is important. It is important. Again, we have checked that this is not important. By mistaken, we have mentioned that it is important. But when we have checked again, we are finding out these two attributes. Closure is same, so we can remove this, and this is important, this is important. Yes, so sometimes rechecking is very beneficial to us. Okay, so in the rechecking we have find out that this is not important for us, right? So the final set we receive is this only. Okay, so this is what set of canonical cover till now, right? Now, in the last step, in the fifth step, we will check the redundancy at the left hand side. So we can see only this functional dependency is having two attributes at the left hand side. So for checking redundancy, we will calculate again the attribute, the closure of AD, A and D. For all the combinations of functional dependency, we will check the closure, right? Okay. So, from this functional dependency set, we will check the closure for all. For AD, we can see here, we are already having AD with us. If we are having AD, we can reduce C. Yes. If we are having C, we can reduce B. Yes, if I having C, we can reduce D. D is already here. If we are having B, yes, we have B. We can reduce A. A is already here. So all the attributes we will receive this. So this is nothing but the closure. Okay. Now, closure of A1, A plus. So here we are having A. Now at the left hand side, no A. AD is here, not only A. So we are not able to deduce anything if we are taking the attribute closure of A. Right. Now D. D we are already having. If we are having D, we are not able to deduce anything from this set. Okay. So we can see that these are not same. It means A and D combination is important. We cannot remove A or D from this combination, because when we are taking only A, we are not able to deduce anything. If we take only D, we are not able to deduce anything. So when we will able to deduce something from this set, when we are having this combination. From this combination, we will be able to deduce all the elements, right? So the canonical cover is, now what we will do, we will write B tends to A, AD tends to C. Now we can see here, we can apply union rule again. You remember when we have started in the first step, we have applied decomposition. So again, when we are writing the minimal cover, we will apply union rule. Okay, so C tends to B, D. So this is the minimal cover we get from our algorithm. So by this way, by following these steps, you can be able to calculate the canonical cover for any question, any type of question. You will able to find out the canonical cover if you will follow these steps of algorithm. Thank you, students. Jai Hind.